is there order in the most fundamental numbers? Mathematical constants, pi, e, the golden ratio, numbers which were deemed special, interesting, and meaningful enough to get their own name. We've all seen them. The most fascinating of them appear in multiple settings across fields of math and science. This prevalence motivated mathematicians to study them, look for ways to calculate them to great precision, ask questions like, is this number irrational? Categorize them, and search for relations between them like the famous Euler equation that connects e and pi. But for most constants, we still don't know of any such relations. It is an open question whether such relations should even exist. Our team, working on the Ramanujan machine project at the Technion, recently discovered a new mathematical structure, which could be a substantial step forward in this adventure. So how does one go about studying constants? How does one evaluate constants such as pi and e? It always involves having a formula. For example, pi can be defined as the ratio between the circumference of a circle and its diameter. But we can also present it by a series of digits. Pi was proven to be irrational, so this representation must extend forever. A better approach for the purpose of exploration is to use a closed-form formula, for example, this integral, or one of many other formulas. The hero of today's story is a specific type of such formulas, the generalized continued fraction. These are two examples, out of many, for continued fraction formulas that converge to pi. Note the patterns they exhibit. Though we would still need to calculate an infinite number of terms if we want to get the exact numerical value, such formulas often have a nice pattern which allows us to understand their behavior and the intrinsic properties of the constants they represent. One of the uses for generalized continued fractions is in irrationality proofs. In fact, the first ever proof that pi is irrational, done in 1761, was via this identity for tangent of x. A more recent example was discovered by Apéry in 1979. A continued fraction representation of zeta 3, which is the value of the Riemann zeta function, famous for its role in the Riemann hypothesis, evaluated at 3. The formula converges so fast as to prove the irrationality of zeta 3. Unfortunately, there is currently no general algorithm to generate useful formulas for a given constant. Historically, they were often discovered by the ingenuity of a select few brilliant mathematicians. Famously, Ramanujan claimed that some of his continued fraction formulas were given to him in dreams by the Hindu goddess Namagiri. Not a very reproducible method.
The question we ask is whether computers can replace or enhance such ingenuity. This is the vision that started our Ramanujan machine project. We develop algorithms for computer-assisted discovery in mathematics. And in fact, we made several contributions toward this vision in the last years. Among them, the first algorithms that discovered new continued fraction formulas that represent mathematical constants, finding hundreds of previously unknown formulas, some easy to prove and some still unproven. Seeing so many formulas for the same constant, we started thinking, could there be a pattern? Is there a hidden rule or a mathematical concept that unites all of them? The first patterns we were able to find were infinite families of continued fractions, which all converge to some fraction of a specific constant. For example, all the fractions in this infinite family converge to some transform of zeta of 2. So we started playing with these families and tried to find different connections between them, until we managed to generalize them. we found a structure that we believe generalizes all possible continued fraction formulas for certain constants. We call this structure the conservative matrix field. So what is a conservative matrix field? Let's start with something you might be more familiar with, a conservative vector field. What is a conservative vector field? It is a function which defines a vector at each point. The conservative part means that if we take a line integral over any closed path, we always get to 0. This is the same as saying if we take the line integral between 2 points, we get the same result no matter which path we take. A conservative matrix field follows the same idea, but instead of moving in a continuous space using path integrals, we now move in a discrete space using matrix multiplication. To move from one point to the next, we multiply by a matrix. Since matrix multiplication is not commutative, if we take any two matrices, then different paths would usually give different results. But we found special matrices that do always give the same result. These special matrices satisfy this equality in every path. It is remarkable that such matrices exist at all. They appear to be extremely rare. So, may I present to you the first example of a conservative matrix field. It is a pair of matrices where each entry depends on x and y. We multiply by mx when moving in the x direction and by my when moving in the y direction. The matrices must satisfy the conservation criterion, which is formally defined like this. Let's see what this means. Start at the point 1, 1. First, to move in the x direction, we multiply by mx, evaluated at x equals 1 and y equals 1. Now, to move up, we multiply by my, evaluated at x equals 2 and y equals 1. We do the same for the other path. The conservation criterion means that we always get the same result. That is, for every point going right then up is the same as going up and then right. Here is another way to visualize it. No matter which path we take from the origin to a point, we get the same matrix. We call this matrix the matrix potential of point x and y. Okay, cool. So we have some matrices that satisfy a nice condition. But how is that useful? Let's start at the origin and move along the x-axis. If you take the ratio of the two values on the right row of the potential matrix, it turns out that when you take the path to infinity, this ratio often converges to a constant. In this case, we converge to E. Every path in the conservative matrix field correlates to a sequence of numbers, which all converge to, in this example, a transform of E. Each sequence can also be expressed as a continued fraction. It seems that many, if not all the continued fractions of E, can be captured by this single structure. And this is not a one-off example. We discovered conservative matrix fields for E, pi, square root of 2 and 3, z of 2, z of 3, and many, many more. Some conservative matrix fields were shown to have more than 2 dimensions. It seems that each constant has a unique matrix field. This field captures all the continued fractions and all infinite sum formulas known for that constant. The matrix field also generates infinitely many more. What applications would there be for conservative matrix fields? First, matrix fields allow us to construct new continued fractions that have much faster convergence. Let's look again at the conservative matrix field of z of 3. Do you recognize this continued fraction? It turns out this is exactly the continued fraction Apéry used to prove z of 3 is irrational. Isn't that neat? We found a systematic way to derive the continued fraction at the heart of his proof. There are many more constants which can be proven to be irrational in this way. Another very exciting discovery is that some matrix fields allow us to find formulas for more than one constant. For example, this conservative matrix field converges to pi. But if we shift all of the points to the right, now it converges to log of 2. Another example is this conservative matrix field that can converge to z of 3 and pi cubed. And this one converges to z of 2 and the Catalan constant.
To summarize, the conservative matrix field structure was discovered just last year, and it's currently a new and wide open field of research. It was found thanks to algorithm-driven discovery that was executed by a large community of volunteers using distributed computing based on the Berkeley Open Infrastructure for Network Computing. Thanks to their support, the algorithm collected the largest ever list of formulas for constants. This list helped us come up with the concept of conservative matrix fields. It has the potential to unify many, or even all, formulas for a given constant. Matrix fields can also introduce order and hierarchy between constants, and hopefully solve long-standing open questions regarding the irrationality of mathematical constants. The Ramanujan Machine Project has a community of supporters, from hobby mathematicians and coders to volunteers who donate their computers to run calculations. Join us. Visit ramanujanmachine.com to learn more.